All right, well, we've come to the last talk in this session. So I'd like to introduce Seth Parker, who is assistant research professor at the University of Kentucky, one of the original team members on my team for virtual unwrapping. And Seth is going to talk to us about scanning at scale. Seth.
So unlike most of the talks you've been hearing in this session, I won't be discussing AI, sorry to say, but I do think I'm going to be discussing something that's very important to the longevity of this project, and that is that we have been discussing today one scroll from this collection. In fact, if we go back a year ago around this time, we were all gathered in Kentucky for another symposium, and I believe this was Youssef's work had just started to come in, and we were all gathered in a room looking at this image saying, this can be done. And now here we are a year later, and it's actually being done, right? We didn't just get one purple word. We actually got many, many columns of text, and it's easy, it feels easy, before these excellent presentations today, it feels easy to look at this image and say, we've solved it. Herculaneum is solved, we can read everything. But it's important to remember that in the last 15 years of scanning, since Dr. Seales did his first scan in 2009, we have scanned 8 intact scrolls, intact pieces. And in fact, only 5 of them are actually scanned at the resolution that we need to be able to recover text, the resolution that we currently think we need. So anyone who's even remotely familiar with the collection knows that 8 is not representative of the full problem. In fact, there are many, many more pieces that we need to scan. And it's not just the computational problem. We do need to go to scale with the computational problem to look at all of the different types of inks, to look at the different segmentation challenges that scan across, or that are representative across the scrolls. But practically, how do we scan all of these scrolls at scale? Julian mentioned that we've been scanning at the Diamond Light Source in Oxford, England, and we've been scanning at a 7.91 micron voxel size, which means that every pixel in these scans is almost 8 microns in size, and a micron is 1/1000th of a millimeter. Practically, that's a lot of data, but also logistically, it's a difficult thing to scan. So I'm going to sort of walk you through what the basics of how this scanning process works for us, and sort of the difficulties in imagining scaling that process to the rest of the 300-400 intact pieces that remain, and introduce some of the options that we have going forward to solve this problem. So first, just some basics of CT scanning for anyone who isn't already familiar. You often have an object, or a CT scan is an X-ray based technique where you're imaging an object by blasting it with X-rays. You have a detector here on the right. The X-rays come through on the left, and then as they pass through the object, they get attenuated by the object, by the material. The X-rays are absorbed by the material. And what you get out the side is sort of a shadow image, the X-rays that weren't absorbed by the object. And this produces sort of the standard X-ray image that you'd get if you just went to the doctor and had your arm broken or something like that. When you add rotation, that's when you start getting a CT scan. You now are capturing the X-ray images from all of the different angles around the object. And from that, here we've just sort of done it 90 degrees, but you would go at least 180, usually 360, all the way around the object. And you can reconstruct from that the internal structure of the scroll. But the difficulty in how we're scanning this is that the Diamond Light Source is not set up to set a scroll on a table in its natural orientation where it's nice and safe. It actually wants the object standing vertically and rotating like this. So there is a process to safely mount a scroll in a vertical orientation, and that is something that we worked on for a decade at Kentucky. How do we safely scan scrolls at the resolution that we need and get pristine CT data out of it? So that process involves, first, going to the hosting institution and capturing a photogrammetry data set for that object. So we set it on a turntable, and we capture photographs from all the way around. And from that, we can create, and not just all the way around 360, we also have to flip the scroll and get the underside, so we have all sides of the scroll from all the way around, sort of a photographic CT scan of a sort. And then from that, we can produce a 2-scale 3D model that gives us the outer shape of that scroll. From that 3D model, we can design a form-fitted case that can safely house the scroll in an upright orientation. This is all computational. We take that 3D model and sort of carve out a cylinder using the shape of that 3D model as the carving point. We then put the scroll in that case and transport it to the diamond light source, mount it onto their sample stage in its upright orientation. And then the diamond light source is particular because it has to get that 7.91 micron pixel size, it has a very limited field of view. So you then also perform what's known as a grid scan. You capture, in this circumstance, 3 by 17, 51-ish scans in pieces, all individual CT scans, but showing different parts of the scroll, starting in the core and working to the outer edges. And using a particular trick of the beam that you have there, you, after 180 degrees, you're actually getting the mirror image of what you started with. So you can take that image and flip it, and now you have a full projection of 6 by 17 grid of CT scans. And you stitch all of those together, and then you run your reconstruction algorithm to get the cross-sections of the scroll. And this is the process for a single scroll. Julian alluded to at the end of his talk that, P-Herc Paris 4 was imaged in 2 halves, sort of an upper half and a lower half. There's actually, if we go back just a little bit, you can see a lab jack at the bottom of this image that the scroll is sitting on. The translation that the sample stage there has is not capable of capturing the full length of that scroll in its vertical orientation. So we actually scan half of it, crank the lab jack to move it into a different position, and then scan the other half of it. So you now have 2 independent scans, which are themselves made up of 3 by 8 scans, that you then have to sort of merge in post and sort of deal with how do we align these CT volumes that are themselves massive compared to the problem that we're dealing with. So it's not trivial for a single scroll even to go through this process. In particular, there are a number of problems, but the key one, if we're thinking about scale, is this fixturing problem. Many of the other problems are computational. The stitching is a large data set, but we can solve that computationally in the limit of time, right? But the fixturing is per scroll. We have to figure out, we have to design a form-fitted case. And to do that, we have to handle the scrolls through this photogrammetry process. We have to be able to see it from all sides to get all of the nooks and crannies of the intense shape profiles of these objects. The case construction, actually designing the cases, can be automated. It's currently manual, but it's all computational. We could automate it. But you still have a quality assurance step. Someone needs to go place the scroll into the case, make sure it fits, make sure we don't damage the scroll when we're doing that. That in itself is a significant amount of time involved in getting that mounting in place. But most importantly, perhaps, is that this just might not work for certain scrolls. This particular one I've highlighted, it's difficult to see in this photograph, has a loose flap on the outside, a loose wrap, which will never be able to stand in an upright orientation without either damaging that wrap or without movement during the scan. It's sort of free floating, which will cause problems in the actual CT reconstruction. So it's not clear that our current method is actually going to scale to the full collection and is not going to be able to support the 300 plus scrolls that we have to deal with. So we've developed in our minds mostly, but in some experiments, what are some options to this? And one way that we can do this is sort of horizontal scanning. Rather than rotating the scroll, we could rotate the system around the scroll. Now this doesn't work at Diamond, where your X-ray source is a beam that's fixed coming from a point in the wall. We have no control over that. But this would be designing a system where we lay the scroll on a table and there is a CT system that rotates around the scroll. This is similar, just like that. This is similar to the medical scanner approach. If you've ever had a medical CT scan, you go and lay on a table and everything sort of happens around you. Yeah, that's how I look in the CT scanner. I don't know about you. Yeah, this is a decent analogy. This is relatively low resolution, the medical CT scanners. This is usually on the order of millimeters rather than micrometers. So there's no commercial system that currently exists that gives us the resolution. So we're really talking about designing a custom CT scanner that's designed to the task of capturing the scrolls at this resolution and if they're full size. And there is some precedent for this in terms of these sort of custom robotic CT scanners. People are investigating this within the medical field and how you reconstruct with something like this. So this is just sort of an example of what you could imagine a more complicated system might be. The key being, though, that all of those parameters, like where the X-ray source is, what its properties are, the detector on the other side, what its properties are, all of those would have to be sort of designed from scratch to fit the scroll profiles that we need to scan. But the idea is you could place, like this blue cylinder on the table, you'd place the scroll on a table in the orientation that suits it rather than which suits the scan, and then you design the scan around it. So really, we're having a custom-built, optimized hardware solution. This has its benefits, obviously. We would just be able to place a scroll on a table and walk away. The negative is that this is relying on a system which isn't currently designed, right? And isn't currently built. But we think it's actually feasible to build. We think all of the technology is there, but there's no commercial application for it, so no one has built it yet. So this is something that we're interested in exploring at Kentucky. We're standing up a new cultural heritage lab there with a X-ray environment, a shielded room, X-ray shielded room, where we can build something like this and begin experimenting with this. So this is one particular option that we have. One of the other benefits I should mention here too is that with this sort of system, you have potentially full environmental control over the scrolls and the environment that you're scanning in. Right? Not only do you design the scanner, but you design the sort of conservation environment that exists around the scan so that you're not introducing sort of damage to the scroll just by the fact that you're carrying it into a lab facility or something like that. A second option is also a horizontal scanning option, but rather than putting the scroll on the table and rotating the system around, you set it on a table, like at Diamond, and you leave it on its side and you scan at this orientation. Now this is typically not great for CT scanning, in particular because while you're scanning from this orientation, the short edge of the scroll, the X-rays sort of go through a very limited amount of material, right? The diameter of the scroll. But in this orientation, they have to pass through the full length of the scroll. So they're much more likely to get absorbed by the scroll as they pass through. And so you have this disparity. On the short edge, you have a lot of brightness. On the long edge, you have not very much brightness, not very many X-rays coming through. And that causes a problem for the CT scans. But if you have a bright enough X-ray source, then perhaps this works. Well, fortunately, we had an opportunity this summer to test this because Julian and Stephen went to the Diamond light source with a scroll from the Bodleian collection, and we tested, can we do the horizontal scanning? So this, again, is the same grid scan technique that you saw before, but now rather than everything in a vertical orientation, everything is shifted. So you have more columns than you do rows. The actual half that we capture is sort of highlighted here on the right, and then the half that we mirror is there on the left. And that gives us something like this. You can see as we start to get end on the scroll, we do start to get pretty significant attenuation through the length, but it's not zero. It's not absorbing all the X-rays, right? So we are getting some transmission through. And so now the question that remains with this is, it seems feasible to do the scanning, but does it actually produce a reconstruction that is of the same quality as the vertical orientation? And is this reconstruction sufficient to then do the complicated work of the segmentation and the ink identification? So this is an ongoing task, an ongoing problem for us, but here's an example of one of the slices from this horizontal orientation. You could get the same thing by taking the vertical orientation and rather than cutting it this way, cutting it lengthwise, but here we are cutting it, or we're reconstructing it from scratch horizontally. And one of the big challenges of this is that in CT reconstruction, your slice size is always the size of your largest axis along the horizontal dimension. So in this circumstance, we have a 23,000 by 23,000 pixel slice that pops out for every single 7 micron step up the width of this scroll. So we have a 24 terabyte data set that comes out just for this one scroll. And that can be reduced by cropping like I did here, but it's not an insignificant amount of data any way you slice it, pun intended. You are going to have lots of data that comes out of this. And dealing with both the reconstruction at scale is part of the challenge here. So from a distance, this sort of looks relatively nice, actually. When I first looked at this, I still think this is doable. There's some open questions that we have to answer. But if you take, for example, a slice from this position here, and then a slice sort of from the end, you're always going to have your best reconstruction quality the closer to the center of rotation that you are. Because sort of like the arc length, the further you get away from the center of rotation, the arc length for a small rotational step gets bigger, right? Really close to the center, 1 degree rotation might only be, 1 millimeter in real life, but way out here it might be 5 millimeters or something. That principle affects the reconstruction quality at the extremities of the CT scan. So that's usually a limiting factor when you're doing a high-resolution CT scan. The larger the diameter, the longer you have to scan, the more rotational samples, the smaller rotational steps you have to take. So what we want to compare here is here, close to the center of rotation, and at the extremity, far, far out from the center of rotation, what does the reconstruction quality look like? So that's what we're seeing. On the left is close to the center of that scan, and on the right is far to the extremity. It's a little difficult to tell at the moment. Again, this is preliminary work. It's a little difficult to tell at the moment exactly how the quality compares here, especially since the actual morphology, the shape in each region is quite different. To my eye, the center is quite sharp, what we expect from the other scans. The outer extremities are smeared, a little blurry, perhaps not going to cut it. The question is, though, can we change these scan parameters that we employed here and improve that quality? And that's the open question that we're sort of still exploring. If we can, then we have a pathway forward to scan at scale for the entire collection that obviates the need to sort of create this custom fixturing solution for every single scroll, which is a significant step. What's not perhaps a straightforward step is that it took 3 hours to do this one scan, which is not that long in the grand scheme of things. And that time is somewhere, that amount of time at Diamond is somewhere in the realm of $8,000 to $10,000. So for the remaining collection, we're talking over $2 million just to perform the scanning on the rest of the collection. That is not an insignificant barrier. And the question now becomes, can we design a custom CT scanner for less than $2+ million? Or can we work a deal with Diamond? They might like to see us more often, who knows? But those are sort of the challenges that face us in terms of the actual CT scanning. And some important questions and challenges remain beyond that. Just however we choose to solve this problem, how do we minimize the risk to the objects should by far be the first question we ask in any of the things that we do with the physical objects. Every time we scan something, we must take a risk by handling the object. But we want to avoid all of the obvious errors and even the non-obvious ones. And so we need to be careful about how we handle the objects and how we think about them. Second is, do we need to scan at 7.91 microns? That's a annoyingly specific resolution that is just at the barrier where you need to go to the diamond light source and not scan in a commercial CT scanner or something that's already available. If we were at 12 microns, then we could and have actually scanned other scrolls, intact scrolls, at that resolution, and it's much more feasible. Unfortunately, at the moment, that doesn't seem like it's going to happen. That's just the nature of the signal. But if we can lower that resolution barrier, it makes a significant difference to our ability to scan these things at scale. And then the obvious next question is, how will we manage these petabytes of CT scans? Both in terms of just simple storage, someone can buy enough storage to store the data, but that doesn't make it feasible to work with. For you as scholars, for us as computer scientists, it's a difficult proposition to scale in terms of that storage solution. So these are the things that we're thinking about, and really beyond just the competition and the virtual unwrapping in its current form, what the next steps are really going to entail. So I want to thank my team that I work with. I do particularly want to thank Stephen and Julian for performing the scan that you saw up here today. They went to Diamond, saving me a trip that I really didn't want to make. So thank you, Julian. I'm glad you enjoyed it. Yeah, thank you all. Any questions?
Good.
Is there a microphone?
Yeah, I can talk.
Okay.
Couple questions. So the 12 nanometer ones that you were wondering about, are those ever going to be made available? Perhaps the question to that could you answer if they were available. And then on top of that, obviously you have 24 terabytes of scan data to do with Bill, right? And maybe it's a stupid idea, and you probably already considered that, but are you able to just make the end the center and then the bottom the center? I'm sure you've already probably done that. Instead of a free scan to 24 terabytes, you'd have to realign. Maybe that just makes
This leads to a scanning a little bit. You can just scan with it, then change your sample to face mode. And save a lot of times.
Oh yeah, and then that one too.
And here's a wish.
Yeah.
I don't-
use the microphone. I'm sorry, I can't hear what you're saying. I don't know whether they can out of the way.
Yeah, well, I can at least repeat that question in terms of the actual scanning. Rather than centering on sort of the center of the scroll in either orientation, can you sort of just put the center of rotation in one spot, shift it to another spot, do the center of rotation there? You can. I actually don't know that it saves you very much. Sort of the beauty of the grid scan is that really the dominant time factor is the movement, like to the different positions, a lot of this. So you really want to minimize the number of movements you do. And you simplify the stitching significantly by doing the grid scan as opposed to sort of this shifted, center of rotation technique.
Well, you just use like higher stem size and also then have a less long time to disclosure. If you do this switching of the standard rotation, because it don't need that high step size. We double the step size, so you could use your normal step size and hardly time.
Right, so when you move the center of rotation and you're not capturing to the extremity of the scroll, something's going out of the reconstruction field of view, that's also going to introduce reconstruction error in that particular section, right? So you really do need a reconstruction that's everything within the diameter if you want to sort of avoid those reconstruction errors. The center of rotation, it could alleviate that, the number of rotational steps that you need there, though. Yeah.
Yeah, thank you. I have a question on the horizontal scan. So
Yes.
if horizontal scan works, do you think it will be possible to use it on the entire community, so to be able to relocate the layers? I mean, even if it doesn't work for the entire scrolls, it may still be enough for a tray of these.
Yes, that is a very good question. If it works on the full scrolls, maybe. The cornici are that much larger in terms of sort of diameter that you really are going to be pushing, I think, the sort of rotational step that you would need to get. One of the concerns I already have with this, let's go back to this, both in the reconstruction quality, but also this image, is you'll notice a flickering effect that you don't get. We're already capturing twice the number of rotational samples in this scan that we were in the sort of the vertical orientation. We don't get that sort of flickering in the vertical orientation, and I'm a little bit worried that that's indicative of reaching the sort of sampling limit of the detector that they have available there, which starts to get into, are we going to be redesigning the system for that? So if we're already reaching that sort of limit with the small rotational samples we're doing here, if we double that or triple that for cornici, are we really pushing beyond what's possible? All open questions. I think tomography on the cornici is a very interesting prospect, as we have discussed before, but it's their form factor is non-trivial.
Thank you for this amazing talk. My question is also, I guess, more of just coming from the outside, looking at this project. I'm sure you guys have considered all the possible particle accelerators that you could use.
Yep.
Why Diamond and other ones that could work?
Right. So Diamond, particularly the Diamond I-12 beam, at the time we began this work, I think this may have changed very recently, was the only one that allowed the size samples that we needed at the resolution we needed. Many have the high resolution, but not the large sample size. This is a relatively, 15 centimeters, believe it or not, is actually a large sample size for most of these environments. Brookhaven is standing up a new beam line that could potentially offer a solution, and I believe the one in France, Grenoble. No, not, was it Grenoble? That's Soleil, yes. They might be making some upgrades to their beam line that would perhaps allow us to scan there, so.
Are they all, do they all require vertical fixtures, or is someone know?
To be seen. Mm-hmm. My intuition is that if the horizontal orientation works in one, it can work in all of them. It's just a matter of getting the right detector set up.
Sure.
So I'll have the mic first, thank you. Could we see the scan of the one in the Bodleian again?
Yes.
That one, yes.
Mhm.
I'm very curious about this white area
Yes.
on the right.
Me too.
And I wonder whether it's, there are some papyrus rolls that have a bit of an umbilicus consisting of two little bits of ivory, one from one end, one from the other end, and nothing in the middle.
Okay.
Or maybe wood in the middle, I don't know which it was. But I wonder whether this is possibly a case of that, and whether looking at the thing actually suggests that that's the case
Mhm.
or not.
So, yes, this is a question I was posing to Federica right before this talk. You can see in this, the contrast may not be quite right, but that white spot is actually in the top portion of this image. It is not straight. It actually curves in some portion, and it's unclear as to why it would do that if it were a harder material. It's a curiosity of this particular scroll that we've not had a chance to really look into. You mentioning, though, that this is a Bodleian scroll did make me want to say that we have now a representative scroll from each of the three major collections, from Italy, Paris, and the Bodleian. So there are others, of course, out there, other pieces out there that we want, but that is, I would say 15 years ago, something I don't think we thought would happen anytime soon. So it's great to sort of be on the other side of that and say, oh yes, we now have a good sampling across those.
My question sort of directly follows up that thought. How cooperative have you found these institutions that come in? Let's say they have one sheet particle beats.
Yeah.
The library.
I would say as cooperative as one would expect a conservator tasked with protecting an object to be. I think everyone has been very interested in the process, and they've been very interested in what we can do, but they've also been rightly concerned about minimizing the risks and making sure that we are actually people who will seek to minimize those risks. So I would say we've been pleasantly surprised with actually how collaborative, and that's only grown over time as these first results have come out. I think we first approached the Bodleian almost 8 years ago about the possibility of scanning these, and at the time it was absolutely not, right? But once this Scroll Prize results came out, once they saw what was possible, and they saw that we had scanned multiple scrolls without destroying them, they were much more willing to work with us for transporting to Diamond and doing those sorts of scans. So no criticism, if it sounds any criticism, no criticism intended in any of that. They've been very collaborative, but cautious.
But could I just ask you, you didn't show them with a bucket of mercury and a knife, right?
Who says I didn't? No, absolutely not. We didn't show up with a bucket of mercury and a knife, but these, for many people, these are unknown techniques, and it does take some time to build confidence, to build the trust, to borrow from Federica's talk earlier, to build trust in the method, and to help people understand how the methodology works. And without that trust, people are rightfully sort of skeptical.
Let me ask you, there is one institution of the four that still hasn't cooperated. Can you tell us about that?
I can't. I'm not going to. I believe it's the British Library, correct? Is the last one, which to my knowledge, again, no criticism intended, the British Library does what the British Library wants to do. They have many of their own resources and seek their own sort of methods for solving these sorts of things. So I'm happy to work with them, though. Yes?
Can I make another point about working with these institutions and trying to get scans of photographs? Doing these scans is actually a wonderful way to conserve the object. These objects are unfortunately subject to physical decay. There are little particles breaking off every time they're moved or every time you look at them, almost. But conserving them is a really good way to photographing them is a really good way to, and this is a sophisticated form of photography, if you like. So they really should be persuadable. I can think of another institution where, this argument needs to be made, and I made it till I was blue in the face and got absolutely nowhere. But now there's a new director there, and maybe things will improve. But it's a very important point to be making to the libraries. This is a way of conserving the data. As long as we can then protect the data, against anything like a Carrington event where there's a solar flare and it wipes out all the electronic data on Earth that we haven't got in a Faraday cage, which I hope all the cloud centers of computing actually know about. I traveled once on a plane with somebody who worked for one of those, and he never heard of the Carrington event, or the fact that it nearly happened again in 2012. And well, Wood have estimated that if it had hit the Earth, this solar flare would have caused $30 trillion of damage to the US economy alone. Estimate commissioned by the CIA from Lloyd's of London. So, you know, we do need to be aware of that as well. But the basic principle is that photography and imaging is conservation. If we can get that across, it would be good.
Other questions?
Let me just say there are very few problems that a few retirements can't solve sometimes.
I was so bad at this all. So like this sounds so magical and annoying that like you know, if you're not use that's the good. Given that there's clearly a lot of funding being thrown at this project, and storage out thing that's done then it has a bit of an environment as well. Is there or has there such amount to the longevity of these sites?
Yes, those conversations are almost constant within the various groups. It is an open problem, both how do we store efficiently and for longevity and for access. Those, in some ways, in terms of archival, digital archival, you can pick two of those things, but not three at the same time. So there are solutions, but none of them are cheap, and most of the money right now is being invested towards the solution of whether this is sort of possible, which I think is the right thing to be focusing the money on now. But at some point in the near future, that funding is going to need to start transitioning into how do we maintain this over a long period of time, and how do we answer all of those questions. But it is being thought about. I wanted to follow up, actually. You asked about the other Italian scroll scans, whether they can be released. I think we'd have to check our data rights agreement for when we did those scans, but in principle, I don't see any reason why those can't be released. They are from a normal CT scanner, so much of the profile of those scans, or intensity profiles, will be quite different, which is an interesting question of whether or not that helps actually in some cases, but it's worth exploring. So.
Yeah, that's great.
All right, well, that concludes this session. I think we're going to take a 30-minute break, and we'll convene at 4 o'clock for our last session of the day. Thank you.